All right, welcome everyone. Well, our webinar today is titled, Which Conjoint Method Should I Use? My name is Brian McEwen. I'm the Director of Client Enrichment here at Sawtooth Software, and I'm joined today by Aaron Hill, the Vice President of Analytics at Sawtooth. Aaron's been with Sawtooth for 19 years. He spent more than a decade heading up our client services and training operations, and he has helped thousands of clients field projects on virtually every topic imaginable. During this webinar, please take note of the Q&A and the chat windows available. The Q&A is going to be the best spot to ask questions, which I'll be monitoring while Aaron's presenting. You can use the chat window if you'd like to send any messages to us privately that you wouldn't want anyone else to see in the Q&A window. We've already answered the questions a couple minutes ago, but a recording of this webinar and a copy of Aaron's slides will be made available within a few days. And with that, we'll go ahead and turn the time over to Aaron.
Great, thanks, Brian. Okay, so today we're going to talk just about which conjoint method should I use. So in the world of conjoint analysis and discrete choice models, there's a lot of different methods out there, and sometimes it's confusing for users about which method should I use for a particular need. So today we're going to talk about which conjoint method would be best for your project, what the different methods do, what makes them different and unique for solving particular types of problems, and then we'll give you some recommendations for the types of projects we think work best for those types of methods. And then we'll open it up for questions so you guys can ask about your particular projects. So if we have questions as you go, again, please use the Q&A function to ask your questions. Brian will moderate some of them. He'll stop me and ask others of them. And hopefully we'll all learn as we go here. So we're going to start out by just talking about the different conjoint methods that are available. There's a lot of different types of methods out there. So Sawtooth offers a handful of different methods across different types of conjoint analysis. There's also a number of other methods that are out there in the universe. So there are lots of ways to figure out people's preferences. What we're trying to do with conjoint analysis is figure out how people make decisions. And there's lots of different ways that you can ask that, lots of different ways that you can quantify it. So we've chosen a few methods that we think work well for a number of different types of situations. But obviously there's a lot of other different ways that you could ask these questions to get similar results. So by no means is this an exhaustive list. By no means is this a list of the absolute best tools out there. There's a lot of tools out there. And we're not going to disparage any of the other ways that you can get at this type of information. So with that, we're just going to spend a couple of minutes talking about the different ways that we offer to do conjoint analysis and discrete choice projects. So starting off, we're going to start out talking about conjoint value analysis. This is our traditional conjoint analysis package. It's available in Lighthouse Studio, and it allows you to do full profile, ratings-based or rankings-based conjoint analysis. It does support card sort, and I hadn't even remembered that we supported it until a few weeks ago. I was teaching a class and somebody had asked about it, and I had to go back and look and make sure that we actually still supported it. But yeah, we do support card sort in there, so you can do single concept, pairwise, or card sort or rankings with conjoint value analysis. Adaptive conjoint analysis is a method that we use for situations where we have large numbers of attributes. So it adapts to the respondent as it goes. It makes the interview questions as informative as possible. Informative is our fun way of saying they're difficult. So as the respondent goes through the survey, they become more difficult because we're asking about things that are more and more likely to be on that line between good products and bad products. And so we can get at what drives those decisions. Then we'll talk about choice-based conjoint. Choice-based conjoint or discrete choice models are models where people make choices between the products. So they're not providing rating scales, not providing rankings or anything like that. They're just looking at different product concepts and choosing which one's the best. Sometimes they're choosing which one's the worst, and sometimes they're giving us chip allocation where they say, in that situation, I would treat 17 of my patients with drug A and 3 of my patients with drug B. So there's a lot of things we can do with choice-based conjoint. and a lot of reasons why we like that too. Then we'll talk about adaptive choice-based conjoint, which is similar to regular discrete choice conjoint, but we're going to adapt the questionnaire as we go. So we're going to ask different types of choices to the respondent and then adapt the questionnaire to get the best possible model for their particular needs. And then finally, we'll talk about menu-based choice, where you're making multiple decisions. And then we'll spend just a couple of minutes at the end talking about MaxDiff, which isn't a conjoint technique, but which we use at Sawtooth and has a lot of similarities to conjoint analysis. So with that, let's jump right in and we'll start talking about our first method. So conjoint value analysis is traditional conjoint. This is the conjoint analysis that's been around since the 70s and 80s. A lot of times when people talk about conjoint, this is what they're talking about. So you have to be a little bit careful, because sometimes when people say conjoint, they mean the broad scope of all trade-off type techniques to get at how people value different bundles of features. Sometimes they're talking about this particular method. So occasionally I'll read a journal article that will say, oh, you shouldn't use conjoint analysis. And what they mean is you shouldn't use traditional conjoint analysis. You should be using something like discrete choice, which a lot of us would also call conjoint analysis. So be careful about the methodology. If somebody asks you, hey, can you do a conjoint for me? It could be that they're talking about this specifically. It could be that they're talking about the range of techniques, and then you're free to do a choice-based instead. So with traditional conjoint, what respondents do is we show them a product profile, and in a typical case, we'd show them a product profile like the one shown here on the screen, and then they'd give us a 0 to 100 point scale, for instance. So we say, hey, how much would you like this car? And they look at this and say, oh, it's a 2005 Honda Accord with automatic transmission, no anti-lock brakes, has driver and passenger side airbags, blue exterior, cream leather interior, and I can get this car for $18,900. And I look at that and say, oh boy, that car, it's a 75 on this 0 to 100 point scale. So, what that means, I'm not entirely sure. It just means that on that 0 to 100 point scale, if they're anchoring it right in their minds, where 100 is definitely would, then this is somewhere around, if we were asking on a 5 point scale, maybe this would be a 4 out of 5. I'm not sure exactly what it takes for them to actually buy this car, but we get a relative preference for, how likely would they be to consider at least buying this car. So they're 75% likely to consider this car for purchase, I think. Okay, all right, so it's a relatively easy thing for respondents to do, but it's got some drawbacks. So let's talk about what makes this work and what makes it not work. So strengths of traditional conjoint is that it's been around for a long time. The math is understood. People understand what it's doing. It's good for both product design and pricing issues. So you can toss price in here, and we're showing things full profile. So we're showing each respondent all of the attributes all of the time. And so for things like price, it shows up every time. And so if people vote based on price, then we're going to get good, strong information about price and how sensitive people are to price. You'll see in other methods that if we don't do full profile, then we start losing the ability to do things like estimate price. So this is good for product design and pricing issues. One other nice thing about it is that traditional conjoint, typically we're coming up with one design or just a handful of fractional factorial designs, and we're going to be asking those. So maybe you have 1 or 2 or 3 or 4 different versions of the design. Each one is designed to be as efficient as possible and gather enough information to get good ratings from each person. But because you have a small number of designs, it makes it really easy to do things like administer it on paper. You can do it through computer interviewing, but you can also do it online. You can actually print these things out and have them rank order them. So back in the 70s, it was very common to print out all of your product concepts. And back in the day, they actually used to call them cards, and then people would sort them. So you'd say, hey, make 3 piles here, put the best ones over here on the left, put the ones you're not sure about in the middle, and put the terrible ones on the right, and then go through the best ones and sort them from best to worst, and then go through the middle ones and sort them from best to worst, and then go through the bad ones and sort them from best to worst. And then you've got a full rank order of those cards. So it's kind of nice because there's a lot of different ways that you can field these surveys. And also, as I mentioned before, it shows them in full profile, so you're never missing attributes. So we're going to show them all the attributes at the same time, and then people are going to make judgments. There's a couple of weaknesses, though. So if we look at the weaknesses of traditional profile, one of them is that, well, it's not even on the slide here, but most of the time we're asking them to use a rating scale, or we're asking them to rank, and ranking, it works fine if you've got 10 or 15 things. It can get a little bit difficult if you've got 20 concepts that we're ranking. It gets really difficult if you've got 45 concepts that you're ranking. So making those types of judgments can be difficult. Using a rating scale appropriately across 20 or 30 concepts is difficult as well. We find that even when we do simple traditional full profile conjoints, even with people like you guys that understand what's going on, it's a difficult task using ratings and trying to make them consistent and understanding what the ratings should be used like. So, if I do the 0 to 100 scale that I showed you earlier, is that actually my intention to purchase the item, or is it a relative thing? Is a 50 actually half as good as 100? I don't know. And so, we're going to use all of these metrics to look at their data, and that's going to assume that if you gave something a 5, it's half as good as a 10, and a 10 is 3 times as good as a 3, but that may not be how they actually use the scale. So we've got some disconnect between how they use the scale and what we're using the data for to interpret it in the back end. We're also using it to predict choices most of the time, and so a lot of times there's a disconnect there as well. We're taking ratings-based data, and then we're assuming that ratings-based data is somehow related to what choices they'll make at the back end, and that may not be accurate. So there's issues with the way we ask the question. There's also a limit to how many questions we can ask. Like I said before, usually we're distilling this down to 1 or 2 or 3 or 4 different versions of the questionnaire, or sets of the tasks that we're going to have people do. And the goal is to get enough information for each of those versions that we could estimate the utilities for that person by themselves if we needed to. And what this means is, in practice, if you've got like a 5 attribute conjoint with 3 levels per attribute, the software is going to recommend that for a robust data set where we've got several observations per parameter that we're trying to estimate, that we might want to ask 22 to 33 choice tasks. Now, if that's the only thing in your study, then that works out pretty well. But if you've got a 15-minute questionnaire leading into the conjoint analysis, then not only have you asked them 22 to 33 conjoint tasks, but they're difficult for the respondents. They've got to deal with a rating scale. How do you allocate 100 points across 33 items? What do you do when you gave something at the beginning 100 and then you see a product that's even better later on? So there's a lot of issues there. And as the number of attributes and levels increases, then so does the length of your questionnaire. So if you do an 8 attribute study with 4 levels per task, which isn't an unnecessarily huge conjoint problem for a lot of the things that you guys want to measure, you're looking at a 50 to 75 question conjoint task, and nobody wants to sit through that. Back in the 70s, you might have been able to do that because you brought people into central locations, you interviewed them, or you mailed them a packet and they could take their sweet time to fill it out and take 2 or 3 days to answer it. Maybe they'd do 50 to 75 of these things, but now you're trying to do it online. You've got a 10-minute window to get them through. Anything longer than 10 minutes, you're paying extra for the panel costs. And so, doing a 75 conjoint questionnaire, it's ridiculous in a lot of different ways. So typically we find that it's not very useful in situations where you've got large numbers of attributes, or you've got a large number of levels within the attributes. Also, one final note on traditional full profile is that it's limited in its ability to estimate interaction effects. So if you believe, as you're setting up these conjoints, we're going to set up attributes, and within those attributes, we'll have levels. So an attribute might be something like brand, and then the levels might be Coke, Pepsi, and Sprite. And then we might have a price attribute, and you're paying $1 a bottle or $1.50 or $2 a bottle. And if you believe that there's an interaction between the brand and the price, for instance, the designer, unless you tell it ahead of time to look for that interaction, it's going to create a design that's optimal for estimating brand on its own. And then it's going to create the design so that it's optimal for estimating the price on its own. But it may not have all the interactions of the brands and the prices. And so you may not be able to estimate the interaction effects because the combination of two of the levels may not have ever even appeared. Okay, so you're limited in your ability, and if you do want them, you may have to specify them ahead of time, or at least have a number of set the number of tasks that people go through so that you're fairly confident that those combinations will occur. So it takes a little bit more processing and time and care ahead of time to estimate those interactions, where some of the other methods will show you don't have to be as careful because we're tossing huge numbers of designs at it. Okay, so when would you use traditional CVA? There's still some reasons why people still use it. So in our survey, we do a survey every year of our consumers, and we ask people how often they do each of the types of conjoint, and then how many projects they do a year, so we can get at a weighted number of projects for each methodology. And there's still 1 to 2% of you guys, 1 to 2% of the projects that you guys are working on, you still might use a CVA. And there's some situations where it works. So the reason that we still sell it is because there are these situations where it still works. So if you've got a small sample size and a small attribute list, one of the nice things about CVA is that I can build a model with just one respondent, right? So obviously I'm not going to be able to project out to the universe with that one respondent, but if all I need to know is what does this one purchasing manager think about these changes we're considering, I might be able to put together a 3 attribute, 2 or 3 levels each conjoint analysis, have Susan take the conjoint exercise, and then I can build a model of just Susan's preferences. So in situations where maybe you're wanting to understand your customers better and you need to understand them on a customer by customer basis, this can work fairly well. Similarly, I can get, and again, this is not on this list, but I can get scores directly because I've got enough data from each respondent that I could just run a quick regression afterwards and get usable scores, or I could just use a counts analysis. So if I've done a careful job creating the survey and I've got each item occurring an equal number of times, I could run a quick counts analysis to determine right then what makes this respondent tick. It's very useful also for simple studies with limited fielding resources. So sometimes we've got projects where you need to take a survey out into the field in places like Africa, and online interviewing or electronic interviewing just isn't possible. So that rules out a lot of the adaptive approaches. I may not want to have millions of versions running around that I need to then coordinate and make sure when I'm printing, I print version 1 as often as I print version 272, and make sure that version 1 gets to males as often as it gets to females. All of those issues, I could put together 3 or 4 CVA versions and then field those instead. And it's a simple question, simple task for the respondents to do. So it may be good in simple projects where you're concerned about people's ability to handle a larger choice type exercise. So you want to find out how happy kids are with a treatment plan for a scary disease. Maybe you do this as a CVA and you put smiley faces down at the bottom to represent the rating scale, and then you read them off to them or show them pictures, and they can answer this type of question. It's also useful in situations where you need to physically create a limited number of actual products. So sometimes we have situations where you really physically need to show people what's happening in the conjoint. So, if you're a tool manufacturer, you might want to actually have people come to a clinic and test out tools. And you can tell them how much vibration is in the tool, or you can tell them how padded the handle is, or how tight the drill bit goes in, or whatever. But it's much better if they feel it, they heft it, they do the drilling or the whatever with the tool, and they see what happens when they've used it for a couple minutes. Wow, gosh, that I thought that would be really good, but it was terrible. Or, wow, that really does stop the vibration. I could drill for days and not get tired with this thing. So if you have a situation where you actually physically need to create mock-ups of your products, then CVA is good because it can reduce down the number of things that we need to look at. It also is useful in situations where maybe you have a lone product in a brand new market. So if I've got a totally brand new experience that I'm offering people and there are no competitors, it may not make sense to do a choice-based conjoint where I'm saying, hey, which of these three would you choose? Because we're not going to produce more than one option. And the respondents, so a choose the best one is never going to be the question that we're actually asking. What we're asking is, hey, how likely would you be to adopt this thing? And so, in some situations, you can do that as a choice-based. We'll talk about that later. But in certain situations, you may be better off asking this as a, how likely are you to adopt question, where you have a 0 to 100 scale, or a I would not adopt, I might adopt if other people do it too, or whatever type scale, where you're getting those answers. So you show them one option at a time, and then they tell you whether they would adopt it or not. Okay, couple more. Volumetric questions. One thing you can do with CVAs, you can show them a product and say, well, how many of these would you buy? So if you're looking at, a lot of times for these types of questions, we would actually just use a CBC question, but there are situations where a volumetric question here might be the more appropriate thing to do, where you show them a product and say, hey, how many of these would you buy? Okay, now we've changed a little bit. How many would you buy now? And so it can be used for that. And then sometimes, finally, a lot of times people use our CVA software not to do a traditional CVA task, but to generate the design, right? So it has a really powerful designer. It uses algorithms that are tried and tested that give you very, very near orthogonal designs. So if you have a situation where you just need a quick design, you can use the CVA designer to get out a nearly orthogonal design very, very quickly and easily. So you can use it just for the designer, or just to analyze data that you got from elsewhere where you want to run an OLS and you've got a conjoint type matrix of information. Okay, all right, let's move on to our next one. Adaptive conjoint analysis. And I'm doing these kind of in chronological order here. So as I said before, there's a lot of drawbacks to traditional CVA. There's some situations where people use them, but there's a lot of situations where it doesn't work. Adaptive conjoint analysis was developed in the 80s by Rich Johnson, who was the founder of Sawtooth Software. And it was a way to get more information. So we like CVA in that it gives us 3 or 4 attributes at a time. Where CVA works is when you've got 3 or 4 attributes at a time and you're trading things off. And we like that because there's simple information. People can make those judgments. But it breaks apart when you have 10, 15, 20 attributes at a time. So what Rich's proposal is that you start out by asking people to rate the different levels. So I might say, hey, here's the 5 brands we're interested in looking at in this study. Rate these in terms of how likely you are to purchase each brand. And so in a computer study, I might go through and say, okay, well, Dell for me is a 5, and Lenovo is a 4, and a lot of the brands that don't exist anymore, Compact, Gateway, whatever, are 2s or 1s, and HP is a 3. And so I can go and answer those questions. And then I say, and that gives me ratings for each of the levels, but I don't know how important that difference was between the best and the worst. So I'm going to ask you a second question where I say, hey, how important is it that you get the Dell that you said you liked instead of the HP that you said that you didn't like? And they say, oh, well, that difference is very important to me. And then we say, well, how important is it that you get, a 500 gig hard drive instead of a terabyte hard drive, or terabyte instead of 500 gigs. And they say, oh, well, actually 500 gigs is probably adequate. Given the range that you're testing, that one's probably only a 4 in importance, et cetera. So they give it ratings on importances. And finally, we ask, how important is it that you get the low price that you want instead of the high price? And they say, oh, that's very important too. And with those two pieces of information now, we can combine them together and get an initial set of utilities for that person. So we can say, okay, we'll take the range there, multiply it by the importance, and rescale those rating scores that we gave initially. And so now we've got ratings scaled by the importance that we can use then to go and create a conjoint model now where we ask the most relevant informative questions. So we're going to start out saying, hey, here's your top 2 attributes, and I'm going to give you something you like and something you don't like on the left side, and something that you don't like and something you like on the right side. And we're going to ask you on a strongly prefer left to strongly prefer right scale, how you feel about those products. And so I look at it and say, oh man, I really like that Dell, even though it has a smaller hard drive. And so I give that a 6. Well, now I learned more about how strong those preferences were for those 2 features and those 2 attributes. And so we continue on, and each time I answer one of those questions, I update my utility so the next question gets better and better and better. And it's nice because we're never showing them all 13, 14, 15 attributes at a time, but we can end up getting good utilities out of it and have them all in one joined model. So I can ask about 15 attributes without having to ever show them 15 attributes at the same time. So it's really nice because it allows us to study models where we have large numbers of attributes. So I kind of went through that process. Here's an example of a pairs question we might ask. So the strengths of ACA is that it allows us to estimate models for large numbers of attributes. So I can have 10 attributes, 15 attributes without wearing out the respondent. We're changing the question types. We find that as we go through the different question types, respondents like having the survey vary a little bit. It learns as it goes. So respondents like it because it's more interactive than a standard conjoint might be. And it's very efficient because we learn not only which item they prefer, but how much more they prefer the thing on the left than the thing on the right. So we get a depth of information that we won't get as I describe some of the choice-based approaches. So with ACA, typically you can estimate a model for each respondent as they go through the survey, because we've got a lot of different types of information and we've got rating scales. So we're fairly confident that we end up with a utility model that works for the respondent with just their data. There are some weaknesses to the ACA though. Like I said earlier, there's kind of a blessing and a curse, and the blessing is that we can handle 15 attributes at a time. But the way that we do that is by not ever showing things full profile. So if there's interactions between attributes, or you need to know the status of one attribute to figure out the value of the other attribute, the ACA may not handle that very well because we're not showing things full profile. Another thing is, even if there's not interactions between things, respondents, if we're not showing all the attributes, they may not be able to assume, like we are, that if the attribute isn't shown, then it's constant across the products. So if I show you 2 computers and one of them's got a really high price and one of them's got a really low price, and the only other thing that's changing is the brand, I might look at that and say, oh, but there's no reason that those 2 things would be, there's no way that would be all else equal in the market. What would really happen is that one would have a tougher case, or a better screen, or it wouldn't come with all the bloatware. And so I make all these assumptions about what's in the products, and I might vote for the one with a higher price just because I assume that there's a bunch of things about it that aren't going to be equal, when we're going to assume that they are equal, right? Because we're going to show them the bloatware attribute later on in the survey. We also find that the way that we do these things and the way that we adjust the utilities as we go, a lot of times for attributes like price, there's just algorithmically there's some issues, and it essentially tends to underestimate the importance of price. So we don't get enough information in the questionnaire to make attributes like price appear as important as they are. Usually we get, attributes that range from the lowest importance as maybe a third of the highest importance, but for things like price, a lot of times it's like 50% of people's decisions, and there's just not a way for the algorithm to recover that major difference. A couple other weaknesses: it has to be done on a computer. So again, if you're fielding in a rural area in Africa and can't have PCs there, then you may not be able to, you won't be able to use an ACA because you have to have it adapt on the fly. And it doesn't match up with how consumers make choices. So it's an unnatural process for respondents. They're giving ratings on things over and over again. They can make mistakes early on that impact the rest of the questionnaire. So there's a lot of ways that that it doesn't quite match up with what we want to do. However, there's still a lot of times where this works very well in practice. So again, this is one of those situations where it's not used terribly often, but when you have a situation that it's useful for, it's really useful. So ACA tends to work well if there's lots of attributes and few respondents. So if you've got 20 or 30 people going to take your survey, or you need to segment by small groups, then ACA works really well by doing those attributes. For situations where attributes are all important.
Something just happened with your audio. I don't know if maybe your cable got pulled out a little bit, but it just got a little garbled on us.
Oh, okay. I didn't change anything, but.
Okay, I think we're back to normal.
Okay.
Thanks.
All right, so when would you use ACA? If you've got lots of attributes and few respondents. If your attributes are all important. So, ACA tends to not work well if you have some attributes that are much more important than other attributes. But there are situations where it's likely that for any given respondent, one attribute is just as important as the next. There isn't really a price attribute per se. So we find ACA used a lot in patient preference research. So especially if you need to find out what a particular patient needs. So ACA sometimes is used for situations where you're not necessarily trying to find out the market demand for a solution, but you're trying to find out, as a patient communication device, how does the patient feel about this, so we can make the best treatment decisions for that patient. And so that patient will go in, do an ACA, we'll get the results immediately, go talk to the doctor about the results, and choose a treatment method that best matches that patient's needs, or at least help them understand how the treatment is going to work with them on items where they showed a lot of concern. It also tends to work well for HR benefits type research, where you've got 15, 20 different attributes that could impact job satisfaction. All of them are important, and it tends to work well there. So, and any situation where you've got large number of attributes and price is not a factor. Okay, all right. Next topic we're going to cover is choice-based conjoint. And most of you are probably familiar with choice-based conjoint, sometimes called discrete choice modeling. Respondents choose between concepts instead of rating or ranking. So we might show them 2 or 3 or 10 or 20 different products, and they choose which one they like best. Alternately, respondents may be asked to allocate chips. So we might say, hey, of your next 10 patients, or of your previous 10 patients, how many would you prescribe each of these drugs? Or you can indicate both the best and the worst. So this is also known as best worst case 3 in the MaxDiff literature, best worst literature. So in these ones, you're asking both the best and a worst. You get a little bit more information that way. But essentially what happens with choice-based conjoint is respondents are given a choice like this, where you say, which would you rather be in 30 years? And we've got different attributes. So you've got income, status, your hair status, and your family situation. So you can be rich or poor or middle class. You can have lots of hair or some hair, or you can be totally bald. And for family, you can have no family, or you can have a very, very large family, or you can have some things that worked out with your family, some things where you're better off friends, right? So you look at these 3 choices here, and you choose which one you'd rather be in 30 years. You also may give them an option none. I'd rather die than end up like any of these people. So this is a typical CBC task. Don't worry, we've never actually asked this of real respondents. I had somebody in a workshop one time get really upset because I had this I'd rather die question on here, and she was worried that I'd actually fielded a survey like this and might have caused somebody to commit suicide. So please don't commit suicide because I've asked this question. But there's a typical choice task. Okay, so nice thing about CBC is that it's an easy task for respondents to do because it's what it's like for respondents in the real world. When you go to the grocery store, you don't rate the boxes of cereal. You go in and you say, okay, well, that one's, you know, I look across them, I weed some of them out, and then I make a choice and I pick up a box and put it in my cart and I move on with my life. And this is what we do most of the decisions we make. When we're driving to work, we never say, oh, well, taking Route 10 is a 7, but taking the bypass, that's an 8, right? We just say, ooh, which one's going to work best for me today? The bypass. I'll try the bypass. Okay, CBC allows for very flexible designs. So we're going to be asking a number of questions, but because we're getting not very deep information from each respondent, we're just going to ask a lot of questions or have a lot of respondents. And so it means that we can end up with very flexible designs. You can do these things full profile where we're showing all the attributes. You can do a partial profile where we're rotating in attributes. You can do alternative specific design. So you can say, hey, how would you rather get to work? Would you rather take the train? Oh, and it comes every 20 minutes and it costs $4 round trip. Or would you rather drive your car, but you got to pay $10 for parking? Or you can take your bike. And biking, there's no attributes that modify that because your bike is your bike, and you know, there's no fees or fines or anything for that. So you can do alternative specific designs where we're looking at different types of products that solve the same situation. You can do chip allocation. So you can say, of your next 10 purchases, you can make these things look like store shelves. We can, because we're coming up with a fixed design typically ahead of time, you can do these things paper and pencil. You can take it out and run it through a different computer program, or you can run it in our software. You can also measure a non-alternative. So again, like in this example I gave here, I gave them an opt-out. They could say, yeah, boy, none of these things are good solutions for me. In reality, usually that's used for things like, yeah, I'd keep shopping somewhere else, or I just wouldn't upgrade my computer at this time, or whatever. Strengths of CBC, it works really well for measuring price and different, new product development, things like that. Anytime where people are choosing between things. So if you have a market where there's already products on the shelves and you're looking at adding a new product or tweaking an existing product, CBC works really well. It can work in the situation I described before, where it's a new product to market and you can show them, maybe 2 products and then give them a very strong opt-out and say, if these were the only products, I probably wouldn't buy this category of product at this time, right? So if you ask it appropriately, you can get at purchase likelihood type questions where you can model, how likely people are to be in the market for the product. Okay, there are some weaknesses of CBC. So we see CBC used a lot in the real world. So probably 80% of our conjoint studies out there are done using CBC or CBC related methodologies. It's best to have large sample sizes. So typically when we're looking at these things for consumer research, we're typically looking at 200 respondents or more. For healthcare pharmaceutical studies, usually we're looking for 125, 150 respondents or more. If your sample size is smaller, you'll need to keep your attribute list small or just make sure that the errors around your estimates are adequate for making the decisions you need to make. CBC sometimes can seem limiting in the number of attributes. If you're flashing up, 5 products on the screen and they have 15 attributes apiece, it may be overwhelming for the respondent. But again, because they're making choices, a lot of times even 7 or 8 attributes on the screen showing 4 at a time isn't terribly difficult, because they often will just go through and say, oh, that one's overpriced, and so I don't have to choose it. I don't have to give it a rating scale, which makes it easy, but so I can just, all I need to do is eliminate the ones that I don't like, and then the one that's left is the one that I choose. But you can do partial profile designs or adaptive CBC to limit the number of attributes if you've got a large attribute list. And it's also, current version in our software anyway is not adaptive. So we're going to ask you some dumb questions maybe from time to time where it's really obvious what the answer is, even though we have a lot of information. you know. And so sometimes when I'm taking these surveys, I get to the end and I'm like, man, why are you asking me this question? Because I've already told you 15 times that I buy this brand at this price and I want this feature. Why do you keep asking me about it? Okay, so when would you use CBC? Typically, I start out with CBC in my mind, and then I eliminate it as a possibility because it has one of these features that make it so that one of these other methods work. So almost always I start with the assumption that it will be a CBC and then shift to a different method if CBC isn't going to work. But typically where CBC does work is studies with relatively large sample size. So, you know, you've got 200 or more respondents, then I'd consider a CBC. Any situation not covered by the first two methods. For pricing research, very often for, you know, brand, price, couple feature trade-off type exercises, CBC is the surefire winner. Research on products that fill the same needs but don't necessarily have the same attributes, like the transportation example I gave earlier. Anywhere where people make measurable choices. It's even been used to model snap judgments on topics like latent racism. So we've had people do CBC studies where they flash up profiles of candidates and they say, which one would you hire? You've got 10 seconds to make the decision. And they look across what looks like resumes and they make snap decisions. And then behind the scenes, what they're actually testing is how much in salary are you willing to give up to hire, you know, a person of one color versus another color, or a female instead of a male, or whatever. So they've used it to try to quantify what is the penalty for, you know, being black or being female in the workforce. All right, next topic, adaptive choice-based conjoint. We're gonna have to zip through the last couple. Adaptive choice-based conjoint is a way to do a choice-based conjoint exercise, but in a more intelligent way. So we're gonna start out with a section that allows respondents to identify the best product, so they build their own product. So you build your own computer, and then stage two, we're gonna show you computers that are similar to the one that you specified in the build your own. And we're gonna ask you a choice task where we say, hey, is this acceptable or not? That's the choice task, is acceptable or not. And then when we've seen them make a number of these choices, we're gonna scan through them and say, hey, is there anything that they rejected every time? Or is there anything that they accepted every time at the expense of everything else? And we're gonna ask you questions about things that are must-haves or unacceptables. And we'll say, hey, it looks like you've never selected anything with feature X. Is that really unacceptable to you? And they say, yep, feature X is unacceptable. And then we just don't show it to them anymore. And then we take the ones that won or that were acceptable, and we put them through a CBC looking exercise where we allow them to choose the best one from those sets. So they're only at that point looking at ones that were acceptable, and then they're choosing the best one. So at the end, they're just looking at the best of the best of the best. And then there's a final section where you can ask calibration questions where you say, okay, well, here's a bad product. How likely would you be to buy that? Here's a good product. How likely would you be to buy that? Here's your ideal product. How likely would you be to buy that? And then we use that to calibrate the utilities so that we can recover a purchase likelihood. So again, you know, if you're looking at a new market item, this is a way that you can get at that new market purchase likelihood. How likely are they to enter this market in the first place? Okay, strengths of ACBC. A lot of the benefits of regular CBC, but can be done with smaller samples and larger numbers of attributes. It's a good choice if you have, you know, 5 or more attributes, especially if they're complex. It works well for measuring price. It accommodates non-compensatory behavior. So after a while, if you say, hey, you know, if I'm doing a housing study, I've got 4 kids, there's no way I'm buying a 2-bedroom house. So after a while, you know, it's going to say, hey, do you really not want a 2-bedroom house? And I say, yep, I don't want a 2-bedroom house. And I can make that go away forever. And it's just going to end up with a really negative utility. So I'd never be predicted to buy into that category. And it's got interaction. So respondents, again, like it better because it's interacting and learning from them as they go. A couple of the weaknesses of ACBC. It's a longer survey. So because we've got all the question types, it makes it a longer survey than a comparable CBC. Currently, there's no support for some of the CBC goodies. So things like chip allocation, traditional none option in the choice tasks, things like that. I can't ask for their best and their worst. So a little bit limitation there on what you can do with it. It's more complex to program and analyze. It has to be done on a computer. It may be overkill for small attribute studies. So if you've got 4 attributes or fewer, you may find that you can do that quicker in a regular CBC than in an ACBC. And it doesn't work very well in situations where all of your attributes are ordered, but you can't attach price penalties to them. So if I'm doing like a computer study, I can say, hey, if you want to choose that hard drive, you've got to pay a little extra for it. But if it's a study on things like drugs, you say, hey, what do you want your cure rate to be? Oh, well, I want it to be, 100% cure rate. Okay, how many headaches do you want? Oh, well, I want the lowest level of headaches. How many, how much nausea and vomiting? None. How much this? How much that? None, 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 none. And so you end up with really obvious answers. And so it just doesn't work well unless you can build some sort of penalty in that makes it so if you want to reduce the headaches, you've got to give up something else. Typically, we make that thing you give up price. Excuse me. Okay, when would you use ACBC? If you've got a large number of attributes. So if you're coming into a study and you say, hey, I've got 15 attributes and the client just isn't budging, then I'd start with ACBC, not CBC. Studies where you need to adapt the attributes and levels. One of the nice things about ACBC is because it's adaptive, I can start out with a list of 30 attributes and I can give the respondent ahead of time a chance to whittle that down. So I can say, hey, which of these attributes do you just not even look at when you're considering which of these products to buy? And they can say, oh, well, I don't use that streaming service and I don't use that streaming service. So I don't care if they're, considered in the mix or not. So you can drop attributes out, you can drop levels out. So I can say, hey, if I'm doing a cell phone plan in the UK or in Canada, then I'm going to show Rogers, Wireless, and Bell. Or if I'm in the US, I'm going to show Verizon and AT&T. So I can have overlapping attributes, but then change the levels based on them not being available to them. So there's a lot of flexibility here with adaptive CBC. And any study where you want to sum the component prices. So if I want to say, hey, I want to have this computer study, but I want to make it realistic. So when I add the bigger hard drive, I actually want the price to go up. Then ACBC worked well because that is a feature that's already built into the software. Okay, last couple I want to cover really quick and then we'll open up for questions. Menu-based choice is good for situations where people are making a number of decisions within a single choice, right? So instead of just making one choice among 3 products, you might be choosing one product and that determines what else I'm buying along with that product. So if I get a basic cable package, then I'm more likely to add on a sports package, but that sports package might have already been included in a premium package. So I might make one decision, I might make multiple decisions. This might be a situation where I've reversed the decision-making criteria, where maybe I'm showing them a product profile up above where it's like, hey, if you are in this situation, which drug would you prescribe? And I've got 4 drugs that are already on the market. So I'm not changing the drugs themselves, I'm changing the situation. So the goal is to understand how the drug choice relates to the patient profile, not the other way around. So with menu-based choice, here's a survey where, maybe I'm just asking them to choose the bundle and I'm changing the prices, but, me choosing option C here may depend on what the price for option B was, right? Similar thing, but a little bit more complex. I might have base models up here and then they're adding options down here based on which base model. The build your own that we use in ACBC is an example of something that might be a menu based where I'm choosing the brand, I'm choosing the price, I'm choosing the hard drive size, and I can vary these prices. So I can have them go through it multiple times, but with different prices, and that might be my exercise. Also, obviously, it's useful for things like fast food restaurants where I want to see how they buy the value meals versus the individual components. Here's another one that's a little bit more complex. Here's one for pharmaceutical goods where they can buy from a single supplier or they can source these things independently. And so there's some attributes that go into the products themselves, but there's also attributes that go into what the supplier looks like, how often they come and visit. And so I can model all of this together in a menu-based choice. Here's one where I'm varying the patient characteristics and the drug characteristics. And so I've got 2 different models here. Maybe this is determined by a CVA design. This is determined by a CBC design, but I'm taking the joint effect of these things to determine which one or more of these drugs I prescribe to the patient. So strengths of MBC is allows you to model interrelated multi-part decisions. So any complex type choice model is supported. So you can do polytomous logit, you can do dependent choices where I choose A and then I choose, the features, B, C, and D that I add to it. I can also model simple choice experiments. So I could take a CBC that I've worked on and maybe I need to make some modifications to it, or I changed the question up above and I can take that into MBC and model it. Weaknesses as it's implemented right now, there is no interviewing platform. You have to create the exercise yourself and then convert the data into a format that MBC likes, and then you can run your models. It's very complex. You have to know what you're doing with MBC because you've got dozens of models running around. Each of them can be specified hundreds of different ways, and so you really need to know your modeling theory so that you can use this appropriately. And also it typically requires large sample sizes. So it's not uncommon, because we've got so many models and so many parameters that we're trying to estimate, it's not uncommon to see menu-based exercises start at 600 to 1,000 respondents, more if you've got a more complex model or you need to segment your markets. Again, when you'd use MBC, situations where the respondent designs their own product bundle. So if you're not controlling the bundle, they are, then you want to consider MBC. Things like telecom, where you're choosing a cell phone provider and an internet provider and a cable provider and streaming services and premium channels, and they're all kind of interrelated. If I can get better streaming services, then I'm more likely to rely on streamed content. I'm sorry, if I get better internet, then I'm more likely to stream content instead of getting it from cable, stuff like that. Anyway, so I think we've covered the other ones. And the final thing I want to talk about just really quickly is MaxDiff. So sometimes we end up with situations where, if it's clear that there's attributes and levels, then we do a conjoint analysis. Sometimes we have situations where we just want to kind of figure out what drives people to do things. So maybe for a benefit study, if you've got attributes like salary and bonus and interaction with the boss, I might do a choice-based conjoint to see, hey, what does that bundle of benefits look like that optimizes my employee satisfaction? But sometimes I might just want to know, hey, there's 15, 20 things that I could do for you as an employee, and maybe I do one or two of them, but they're not really attributes. I just want to know, would you rather have a company party, or would you rather, have better snacks in the break room? And so in those situations where I've got a list of things that aren't attributes, I might do a MaxDiff instead. And MaxDiff just allows people to tell you which thing's the best from a subset of the items, which thing's the best, which thing's the worst. And then essentially it's like a one attribute conjoint. And then we convert that into scores where we predict how likely it is that that's their best thing. Typically we showed between 2 and 6 items at a time, so you can have 30 or 40 items in your experiment, but we're only going to show them usually 4 or 5 times per task. We rotate through them so that each item occurs 3 or 4 times, and then we are able to create these models that are ratio scaled. So you can look at the things and say, okay, well, if something scores a 10, it was twice as likely to be selected as the best as something that scored a 5. We find that this is easy for respondents to answer. It's much easier for them to do this than it is for them to do like a rating scale of 40 items or trying to rank 40 items. You can do fixed design, so it's pretty easy to put together a simple design and then use that for each of your respondents. Typically, it's better than standard rating or ranking exercises. So whenever you're in a situation where you're looking at a rating scale and you think, gosh, last time I did this, I ended up with 50 million ties. Everything was rated as a 5. And so we really didn't get much out of it. Think about doing a MaxDiff instead. Weaknesses of MaxDiff, it does require fairly large sample sizes because like CBC, we're going to need to borrow cross respondents to get our models. The resulting model isn't additive, so I can tell you whether they want a exercise room or a break room, but I can't tell you how happy they are if you give them an exercise room and a break room. So we can't do that. Where you'd use MaxDiff, anytime you need a replacement for a rating scale type question. For product development, we often use it at Sawtooth to figure out, hey, which features should we stick in next? Maybe it's not changing the price or anything. We just want to make sure that we're making people happy when we're adding new things to the software. It's very often used for advertising statements, for political statements, things like that. You can structure this so it's conjoint-like. by putting in prohibitions. So if you have attributes, maybe you have 5 attributes, and you've got these things, but you actually really want to measure them in relation to each other. So maybe you've got some break room related attributes and some exercise room related attributes. You can put in prohibitions, so only one break room thing can show up at a time, one exercise room thing can show up at a time, but then essentially you treat it like a MaxDiff when you're analyzing the data. Okay. Excuse me, I'm sorry. So finally, there's some extensions to MaxDiff. You can feed MaxDiff results into an ACBC for their attributes, so you can create scores on the fly. To do that, to do follow-up questions, so you can say, hey, how come you rated these things as your top items? How come you rated these things as your bottom items? There's different ways that you can deal with larger lists. So typical MaxDiff, like I showed you before, works well if you've got 20 or 30 items, not so well when you've got 100 items. So there's a couple ways that you can deal with that. You can do what's called a sparse or an express MaxDiff, where we're either just showing each item a small number of times and then relying on large sample to overcome it. Or you can do an express where you can show each respondent a small number of items, but still, 2 or 3 times a piece. And so you get good data on those, 20 or 30 items, but no information on the rest of them. And that can be useful in situations where it takes a while for them to learn about the items. And thirdly, there's a banded option where you can have the software as respondents are going through it. The first, maybe 20, 30, 50 respondents are going to get a random draw of your 100 items. So maybe we're only showing them 20, but they're getting, 20 randomly of the 100. But as respondents once you start getting past the 20, 30, 40, 50 respondents, we're going to look at the first respondent and say, okay, well, how likely was it that this thing was the best item? And we're going to draw those best items to include for the next respondent more often than we draw the worst items. And so what happens is things start percolating up and down. So the items that get rejected as worst over and over again will start not appearing in the designs, and we're going to show the best items more and more often. And so by the end of the experiment, you're just looking at the best items. So those are some of the extensions to MaxDiff. And we got a quick graph here that you can look at for some ideas on which method you might want to use. If you call us, those are the types of things that we'll look at. And with that, we're done. I think we have time for a couple questions here. So we will open it up for questions.
Okay, thanks, Aaron. We had a lot of questions on sample sizes. Maybe you could just give just a brief overview of just some rules of thumb. Sample size is a tricky thing. We've got technical papers on it and things like that, but maybe just spend 30 seconds just to give a brief overview of just kind of rules of thumb for the various methodologies.
Yeah, so quick rules of thumb. If you're using a method that I said worked well with small sample sizes, typically it's because we're getting enough information from each respondent that we can estimate their models independently. So we may actually use a method that like hierarchical Bayes that borrows across respondents, but we have enough data to get their data individually. And so if you're using like CVA or ACA, or in some situations ACBC, your sample size needs are equivalent to what you'd need for the rest of your survey as far as projecting to the population. So then the only concern is, do I have enough people to project to the population of interest? For CBC, you've got an additional thing you need to think about. So it's not just that I need enough information to project to the population, or I need enough people to project to the population, but I also need enough information to make the model work in the first place. And with CBC, a lot of times we're only asking like 10 choice tasks of a respondent, and so we may not get enough information from any one respondent to estimate their model. So if we tried to take just one respondent's data and run it through the estimation technique, it would fail because there's just not enough data. So we have to borrow across respondents. So then not only do I need enough respondents to project to the population, but I also need enough for the math to work and for my standard errors to be low enough. And so CBC includes some tests that you can run to tell you in aggregate how much error is in those estimates, so that I can get them down to a reasonable number. So it's going to depend on things like how many questions I'm asking the respondents, how many concepts I'm showing in each of those tasks, how many attributes and how many levels are in those. So if I've got an attribute with 15 levels, then, you know, I'm going to have to make sure that each of those levels shows up an adequate number of times. So what's good for my 2-level attribute may be terrible for my 15-level attribute, because each of those levels needs to show up as many times as the 2-level attribute level showed up. So there's some tests that you can run in the software to figure out what sample size you need. Just general rule of thumb. Brian, you're on mute, so.
Thanks. Yeah, I just wanted to remind people that we will be sending out a recording, and we'll give you a copy of Aaron's slides. So especially on that cheat sheet slide towards the end that kind of lines them all up for us. Don't try to write that all down or anything like that. We'll be sending you a copy of it. We'll go ahead and stay on. There's a couple other questions still coming in, but we've hit our hour. So you can keep typing in questions. We'll keep answering them, but we'll go ahead and wrap things up here. If you're interested in the next webinar, that's going to be on August 19th. Keith from our consulting group is going to be presenting on drivers analysis. He's going to be showing us how to do it both very badly as well as how to do it well. So make sure you sign up for that. Thanks again, Aaron, for the presentation, and we'll see everyone next time.
Thanks.